Good morning everyone. So welcome to the day 2. So in this session there are 4 talks. The first talk will be by Professor Arghya Choudhury, current status of R-parity violating supersymmetry.
Okay, good morning everyone. Am I audible? Okay, thank you. So first of all, I want to thank the organizer for giving me the opportunity to present our work here. So basically today I'll talk about what is the current status of the R-parity violating supersymmetric scenarios. What are the phenomenological? So basically this talk will cover how we can generate or what is the present in the present context data. What are the constants coming on the neutrino masses and mixing on behalf of the RPV SUSY models. Basically yesterday Arpita gave a detailed talk on this issue, so I will only mention about key features of these things, and then there are other phenomenological implications. I will also talk about the LHC constant coming from run 1 and run 2 data, and few high luminosity projection on RPV searches. Then I will summarize. So this is the R-parity violating superpotential. You see the first 3 terms, they violate the lepton number by amount 1, and the last term UUD coupling, they violate the baryon number by amount of 1. So in contrast to the RPC supersymmetric model or PMSSM you are aware of, the main difference is now LSP is not stable, LSP is unstable, and this is not a good candidate for the dark matter anymore. But if you allow all the couplings at a time, means lepton number violating term and the baryon number violating term, then there will be proton decay, and a robust constants basically comes from the product of lambda prime and lambda double prime. So that will restrict us, either you take lepton number violating term or the baryon number violating term. So now from this lepton number violating term you can generate the neutrino masses, because in the PMSSM, R-parity conserving PMSSM, there is no neutrino masses are mixing. Without invoking the dimension 5 Weinberg operator, you can generate the neutrino mass and mixings. And there are 3 terms here. So only this is called bilinear term. This can actually generate neutrino masses at the 3 level. And this bilinear term, lambda and lambda prime, all the 3 terms, they can contribute to the neutrino masses at the 1 loop level. And if you redefine the basis for the suitable choice of basis, basically you can start with the only lambda and lambda prime term, not with the bilinear term. That has been shown, but they will eventually shows up at some other energy scale if you do the renormalization group running. That has been also recently shown by Shobboshachi and Jaydeep. And these terms, bilinear terms, basically they are generated from the trilinear couplings. On the other hand, if you start with the trilinear, only bilinear term, then the trilinear interaction which is similar to lambda and lambda prime, they can be generated from the bilinear term also. So this has been shown by an earlier paper by Vishrup Mukhopadhyay and Saurabh Rai. So basically you can think of the bilinear is the most simplest one model. So I will talk about the bilinear RPV SUSY model first. So the 3-level term, basically that will mix the neutrino and the neutralinos. So it will be eventually a 7x7 matrix, and if you diagonalize it, so that will give rise to the masses to the neutrino. And if we consider the normal hierarchy scenario, so the nu 3 will be mostly getting mass from this 3 level, and it will also get correction from the other loop correction. And for the second one, that will get mass from the BB loop, where neutrinos and the neutral Higgses, they are mixed by this bilinear term. And then again the lightest one, neutrino, they basically get mass from the epsilon B loop. Okay. So these are the simplified formulas with some, when you consider all the masses are at the m tilde, then basically the contribution depends on the product of the couplings and also tan beta, eventually cos beta or tan beta. You can, so basically yesterday Arpita gave a detailed talk about how we have done a parameter space sampling using some likelihood analysis using Markov chain Monte Carlo method. Basically, the key points are we have considered the different neutrino oscillation data, the latest global fit of different neutrino oscillation data, and the recent mass and signal strength measurements of the Higgs, low energy observables like B2S gamma and BS going to mu plus mu minus, and the relevant constants which are coming from the LSC data. So basically then we have projected out the 1 sigma and 2 sigma parameter space of the bilinear parameter space. So this is basically the marginalized posterior distribution of our bilinear parameter space. So you can see there are 9 bilinear RPP parameters. All the parameters are basically constant from this fitting. Okay, some parameters they have nice correlation. Okay, if you are interested for the detailed, you can look at this paper. And now if we consider only trilinear model, if we consider only lambda, then it is difficult to fit, only it will fit one mass. But if you consider only lambda prime model, that will also not fit all the parameters. But in a recent ongoing works, we are actually fitting, if we consider both lambda and lambda prime scenarios, then it can be fitted, and the preliminary results have been presented yesterday by Arpita also. So now coming to the other phenomenological implication of this model. So basically these RPP models from the lambda prime coupling or lambda coupling, they will contribute to the different low energy observables. For example, B2S gamma contribution may come from lambda prime coupling or lambda double prime coupling. So basically, if you from those measurement you can constrain these values. Similarly, BS going to mu plus mu minus, you can also get relevant limits from the measurements on the product of lambda prime or lambda prime. So all these limit also basically depends on the say relevant S particle masses, for example neutrino masses and the squark masses. And now the LSC is putting more and more stringent bound on the squark masses. So the product, the limit on the product is getting little bit weaker. And eventually you can have mu to E gamma like L to L gamma scenarios or L to 3L scenarios, lepton number violating scenarios, and meson oscillation. They will also put constraint on the RPP couplings. For example, neutrinoless double beta decay, there is a recent paper from Bhupal Dev. You can see the lambda prime and the lambda prime coupling, they also put stringent bound. So these are the LS constant, these are the mu G minus 2 allowed region for different choices of mu and tan beta, but in some places the stringent bound is coming from the product of from the values of lambda prime. It can so now the leptons in the RPC scenarios, the muon G minus 2 contribution basically comes from the muon LSP loop or charginous neutrino loop. But now the leptons, they are mixed by these couplings, so now you can have more contribution from more diagrams. So basically lambda loop from this loop, basically product of lambda and lambda, they will contribute, and there can be similar contribution from the lambda prime coupling also. So there has been a few years ago, Amit and Shobboshachi, they did an analysis on this thing. So now coming back to the collider scenarios. So now this LSP we are talking about, they will not give missing energy signal in the collider now. But so the conventional analysis which relies on the missing energy, that will not work for the RPB scenarios. But what will happen, now the LSP is decaying into either leptons or jets. So when your lepton and jet multiplicity will be increased, and depending upon whether it's a prompt decay or it's a long lived particle, you can have different kind of signals in contrast to the RPC scenarios. For example, here I have shown you some example. You can produce the LSPs directly, here the Higgson's production, and they will decay eventually some quarks. Or you can produce the NLSP like Gluino, which is eventually decaying to TT bar chi-ion 0, and chi-ion 0 is getting decayed via this UDD coupling. So there are a lot of quarks and say a lot of heavy jets, and so basically the signals are altogether different from this. So when the lepton multiplicities will be increased, then you can expect that the limits compared to the RPC that will increase, but when the lepton multiplicity is less, or when we are seeing maximum number of jets, then the limit will be reduced to your conventional limit. To summarize the limits, say final states, if it is consist of high jet multiplicity, which is basically coming from say gluino pair production, or gluino is decaying into QQ bar chi10, or stop where you are considering decaying via lambda prime or lambda double prime. So there are large number of jets and at least one lepton and 0 to 3 B jets tagging. So these are the results from the atlas. So you see now around 2.2 to depending upon the scenario, the gluino they have excluded for the gluino going to QQ bar chi10. Even the stop is around 1.5 TeV they have excluded from this analysis. And when this is the LSP is going to the say QQ bar L and say or this via this lambda prime lambda coupling, chargino is decaying into a LLE coupling. So there will be more leptons in the final states, which will be reflected here from the gluino production. You see the limit can be enhanced up to 2.4 TeV, and this lambda IJK coupling, if the third generation is involved, means you will see tau in the final state. Then for the tau in this final state, the limit is little bit less. And this is coming from the chargino neutralino production. You see the RPC limit is around 1.2 TeV, but it is around 1.6 or so almost 500 GeV larger than the RPC limit. And this is again the green line is for the when the third generation is involved. So instead of 1 to 1, so we are considering basically I33 coupling. Now, so let's talk about the top squat limit. Top RPC limit is around 1.2 TeV, but if via lambda prime coupling, it can decay through this LQD operator. They can have a two-body decay, and if we see at 2 lepton plus at least 1 B and 2 jet, then we can see that the stop limit can enhance up to 1.9 TeV, which is much more stringent than the RPC scenario. And when it is decaying into 100% branching ratio to B tau, these scenarios, these limits are typically around 800 GeV. So then again, this is not seen in the RPC scenario. You can fully reconstruct a chargino when in the bilinear RPV model. So basically, they have reconstructed at least one chargino, where chargino is going to a Z and a lepton, and that Z is going to an LL bar pair. And then at least they have reconstructed one chargino, and the limit is depending upon the branching fraction of the Z, because it can also go to W, L or Z neutrino or Higgs neutrino. Depending upon that, it can have a limit. When the branching ratio is 100% of ZL, the limit is around 800 to 900 GeV. So yesterday, Shagota, Shankha and Silpi, they discussed about the long-lived particle. Shankha also showed some supersymmetry contribution there. So the LLPs, long-lived particles, are very common in RPV, and it is common in a sense either you reduce these values of the lambda or lambda prime couplings. The couplings are very small, or the mass gap between the lightest supersymmetry particle, the NLSP-LSP mass gap is very small. So you will have different kind of signatures which has been discussed yesterday in great details, like displaced vertices, disappearing tracks, and non-pointing photon, etc. So basically, you can see the diagrams where we are producing Higgsinos and the gluinos, the NLSP, which is further decaying into a QQ bar LSP. Here chi10, and where this decaying, so you are seeing multiple quarks, they are decaying into multiple quarks, and from the displaced vertices, the channel, they have, depending upon then again this limit will depend upon the light time. So what we see that This is typically when the lifetime is 0.03 nanosecond to 1 nanosecond. The limit is around 1.6 TeV for the charginal neutralino production. And if you produce the gluino production, when the gluino is around, if you fix the gluino mass around 2.4 TeV, then we can exclude neutralino mass between around 2.5 TeV. Okay, depending upon this mass. So this is from Atlas results, but Biplav and Prabhat has done a recent analysis where they have projected the limit at the high luminosity LIC. If you are interested, you can look into this paper. And basically in a recent article we have categorized all those results and different phenomenological applications in these papers. If you are interested, you can look into this. So before finishing this, I want to discuss what is the high luminosity prospect of this RPV scenarios in few scenarios, because the limits on the electroequivalent sector is still very less. So we basically try to probe what will be the future limits of the high luminosity LIC. So when we consider there are 9 non-zero values of lambda ijk, and that can give rise to different final states. So I am just showing one final set here, but we have considered all the scenarios there. So when the electrons or muons are only involved, then you will get the most stringent limit, and this is the current LSC bound around 1.5 TeV. So if we implement some machine learning analysis, and we showed that this 1.5 TeV bound, it can be reached up to 2.3 TeV at the 3000 FEM1 inverse if we consider charginal neutralino production, and for here it is decaying only into the first 2 generation leptons. And from the lepton pair production, the current limit is around 1.1 TeV for the first 2 generation, but the machine learning based algorithm will enhance this limit by around 700-800 to up to 1.8 TeV. Okay. So now these limits we are talking about when it is decaying into leptons, but if it is decaying into a quarks, like baryon number violating UDD type of couplings, with Rahul, Biplav, Indrani and Najimuddin we did a work earlier. So the limit is, this is the green region is the RPC projection at the future LSC, but you still see that the limit is around, still is high luminosity projection is to sigma projection will be around 600 GeV. So here we have considered different scenarios, different decay modes, but in most of the cases the limits is lying between 500 to 700 GeV. So one more thing I want to mention about here, in many diagrams you will see that this low LSP mass region for here or in this region, when the LSP mass is very small, still we are not able to probe to this region. To summarize this, so basically I have discussed various phenomenological implications of RPV-SUSY scenarios, and the electroic sector is still unconstant, and it can address many issues like muon G-2, neutrino oscillation and flavor anomalies. The LSC searches are quite exhaustive, but there are still rooms for the improvement, and regions with the light LSP, basically typically mass, when the mass is less than 100 GeV, the region is still unexplored in many cases, and this needs special attention like deep learning or jet substructure or reconstruction of the neutralino. We can implement different analysis, and that should be looked into in more details. That's all.
Thank you, Arghya, for the detailed discussion. So,
yes.
Yeah, questions.
You mentioned that one of the essential features of R-parity violating scenarios is neutralino decay and therefore no met and visible particles. I just want to remark that this is not fully accurate, because particularly in the bilinear R-parity violating scenario, there is mixture of neutrinos and neutralinos,
Correct.
as a result of which a neutralino can decay into a neutrino and a Z. And the Z decays with its 20% branching ratio into neutrinos.
Correct.
So, in fact, there are met and without met signals at the same time, whose correlation may reveal important features of the scenario.
Absolutely correct. Absolutely.
That's all.
But I was talking about in general, like in RPC where you have a neutralino and the typical missing energy in most of the cases it will be not there, but in these cases it is correct. Yeah, that's best.
So,
Will be enhanced
20%. So
yes,
actually it can be substantial
Yes.
met signals also.
correct.
Okay, any more questions? If not, let's thank the speaker again.